Hi folks, I'm making this video here to help you out with your homework here. We're going to talk about problems 10, 11, 12, and 13 on the Unit 4 homework over electricity and electrical phenomenon. So number 10 here, what I'm reading, let's see, it says an electron is accelerated by an electric field of magnitude 275 Newton per Coulomb. So number 10, we've got an electric field, which in my example says 275 Newton per Coulomb, but on other people's homework this value may be different. And it says to find the acceleration of the electron. So, all right, the electric field here, I'm going to go ahead and draw a vector to represent the electric field. I'm going to draw that to the right, which is perfectly fine. I could actually choose any direction I want to draw that field. And because this problem is about an electron, I'd probably start by drawing a negatively charged particle. Now, first thing I realize within my picture here is that I'm going to move this over here now, and you'll see why in a moment, is that the force direction on the electron is going to be to the left. Oops. Because of how the electric field is defined. The electric field direction is defined as the force direction on a positively charged particle. So if I put a proton at this point in space, the force would be to the right. Electron would have a force in the opposite direction. And this force we can calculate from the definition of the electric field. Remember, the electric field strength is equal to force per unit charge. So if I take the charge and I move it over to here, and I actually, with my computer, can do that pretty easily. If I take this and just multiply both sides by Q, now what we have is that the force is equal to charge times the electric field strength. So the way we start this problem is by multiplying by the charge of an electron, 1.6 times 10 to the minus 19th coulombs, times the electric field strength, which in my example would be 275 newtons per coulomb, but again, this number is going to vary depending on your homework problems. And this is going to give the net force on the particle in newtons. Now, the question says to find the acceleration. Well, by Newton's second law, remember, net force is equal to mass times acceleration. So the net force is what we're calculating here. That number is going to go here. The mass, you look this up, this is the mass of an electron. And I'm going to let you folks look that up. Mass of electron in kilograms. And then you find the acceleration. Now, don't be surprised if you get just a ridiculously big number. Like if you get something like 10 to the 10th power or 10 to the 12th power, that's fine. This is going to be a massively large number when you find that acceleration. All right, part B, where it says use equations of motion with constant acceleration, yada yada. All right, I'm going to ignore those directions, and I'm just going to look at the question. Find the speed after 1.15 times 10 to the minus 8th seconds, assuming it starts from rest. So I'm going to attack this just like I attack almost every question that I'm asked about in motion with a graph, right? A velocity graph. Oops. Now, this electron starts from rest. And again, remember, this is a graph of velocity against time. And the velocity describes how fast it's moving. So at t equals 0, this electron is not moving yet. It says it starts from rest. And then they give a time in this question. It says, in my example, it gives a time, a delta t of 1.15 times 10 to the minus 8 seconds. So in your homework, this may be a different value, but everybody will have some number here. And that's going to be this horizontal distance on the graph. And then the vertical distance is the velocity at that time. And when they talk about constant acceleration, what they mean is to assume this is linear, which it would be. Now, in this graph, this is the delta t, and this is the velocity, and the acceleration is equal to rise over run. So that's going to be this distance, which is our final velocity, divided by this distance, which is our delta t. Right, so long story short, this number will go here. This is what you're trying to calculate. This is the acceleration that you found from Newton's second law here. So that's enough to get that problem outlined. All right, I'm gonna now talk about number 11. Get rid of this stuff. All right, so number 11, let's see, it says a light bulb used in a computer projector has a resistance of 23 ohms. What is the current when it's operating at 120 volts? So I would start this with a circuit diagram. All right, the 120 volts. And again, on you folks' homework, that might be a different value. Mine says 120, but other ones may say something else. The circuit diagram might look something like this. Right? So this is the picture for voltage or potential difference. Remember that the positive terminal, the long post here represents the positive terminal, and this one the negative terminal. And then the computer projector has a resistance of 23 ohms. Now I don't have to draw the actual projector, but this is the symbol for resistance right here in a circuit diagram. So this would be the circuit diagram that kind of describes this problem. In this example, it says this resistance is 23 ohms. Yours on your homework may be a different value. And then it says the voltage is 120 volts. Yours may say a different value, but that's the potential difference between these. So basically this symbol means potential difference. Now I always like to color code the potentials. This is all conducting material all along here. Right? And remember my IFAX video, one of them is this. A conductor itself is an equipotential. So this would all be one potential. This would all be at the same potential up to that point. Same thing on the other side. This is all conducting material up to this point. So I'm not going to bother, I'll just leave it black, but that's all one potential. Now you'll notice that red to black represents a 120 volt potential difference. And look at our resistor here, red to black. So we know that the potential difference across that resistor is 120 volts. So when we write out Ohm's law, V equals IR, the potential across the resistor is the same as the battery. So this value is going to go here. And then the resistance is given, that value will go here, and then you'll solve for the current. That's a pretty short question there, so let me take a look at the next one here. Number 12. Let's see, the resistance of the skin of a person is typically around 70,000 volts. How much voltage would be needed to cause a current to flow in that finger? So let me get rid of this. We don't really need a picture, I think, for this question. Get rid of this too. Okay, basically we're given a resistance in this question. In my example, 70,000 ohms, but yours might be something different. And we're given a current, 0.001 amps. Again, that's what mine says, but yours might say a different value. And we're asked for a voltage. So this is just an Ohm's law question. Voltage equals current times resistance, where they gave us a resistance and a current, and then you can calculate the voltage. All right, number 13. It says, again, let me get rid of this. Let's see, it says a 390 ohm resistor is connected to a variable voltage power supply. All right, so I'm going to write that down. I've been given a resistance, 390 ohms. Yours, when you do your homework, this may be a different value. That's just what mine says. All right, and then it says what voltage is necessary to cause a current in a 0.4 resistor. So I'm going to start again with a picture of a circuit that has a voltage, which I do not know, and a single resistor. Now, if you watch some of my other videos on this, I posted several videos where there's multiple resistors in parallel. You know, if I had another resistor in parallel, it might look something like this. In this example, we don't have that. We just have a single resistor. And again, this is the positive terminal, the long one, and then the negative terminal. And then I always color code the potential. This is all one potential. And again, this is coming from my IFAX video. If you don't know what I'm talking about, go back and review that video. One of those IFAX, I can't remember the one, probably number 2. Because there's no electric fields in a conductor, then the conductor itself is an equipotential. Right? So this would all be one potential. So now this is just a matter of, let's see, what do we know here? Part A, it says what voltage is necessary to get a current of 0.4 amps. So in question A, we're given a current, 0.4 amps, and we're asked for a voltage. So we just apply Ohm's law, V equals IR, and we're given an I, and we're given a value of R. For part B, it says what current will flow if the voltage is 12 volts. So in part B, they're asking for a current, and now the voltage they're saying is 12 volts. So again, this is an Ohm's law question, so voltage equals current times resistance. The voltage is the 12. The current we're calculating. It's the same resistor. So this, in my example, is 390 ohms. Is still good. That value would go there. And then you would calculate the current. So I think that's enough for this video here. There's a little help with those 4 problems. Hope it allows you to get through them. Have a great day.